Friends, let us continue with the 13th lecture on module 2, where we will continue to discuss dynamic analysis to obtain natural frequencies and mode shapes of a dynamic system. In the last lecture, we discussed the first method, which is the classical eigensolver method to obtain natural frequency and the corresponding mode shape for an MDOF system. In this lecture, we will discuss about another numerical method, which is influence coefficient method to obtain natural frequency and mode shape for a multi-degree freedom system model. What are influence coefficients? Influence coefficients are nothing but flexibility coefficients of a given system. If flexibility is expressed as small f, it has a relationship with stiffness. For a given system, using Newton's force method, we can derive stiffness matrix for an MDOF system. So, just take an inverse of the stiffness matrix, it will actually give you the flexibility, which is influence coefficient matrix. But in this lecture, we will explain you how to obtain the influence coefficient matrix directly without inverting the stiffness matrix. So, we will take an example of a 3-degree freedom system model. Mass being all equal and stiffness being all equal, where the degrees of freedom are marked as x 1, x 2 and x 3. So, flexibility is to give unit deflection and find the force. So, let us say I want to draw the first degree. So, give unit deflection and find the force. So, this is going to be k times of alpha 1 1, whereas this spring will oppose, is going to be k times of alpha 1 1 minus 2 1. We will have the same value, but opposite in direction. This bottom spring will oppose k times of alpha 2 1 minus 3 1. So, this spring will have an opposite direction of the same value. So, you must realize that the second subscript in this derivation is all 1, meaning that we are giving unit displacement at the first degree. Similarly, I can do for the second degree. So, I give delta as unity here. So, in that case, this spring will have a force which will offer alpha 2 2 minus 1 2 this will be opposite, and this will be stiffness of alpha 1 2, and this will be stiffness of alpha 2 2 minus 3 2, this will be opposite. Similarly, we can do for the third degree. Let delta be unity. So, this will be k times of alpha 3 3 minus 2 3, this is opposite. This will be k times of alpha 2 3 minus 1 3, and this will be opposite, and this will be k times of alpha 1 3. So, this is first degree, this is second degree, this is third degree. So, let me write down the equations based on this. Let us take the first figure, that is, this is the master figure, this is figure 1, this is figure 2, this is figure 3. Let us take figure 1. So, figure 1 was unity here, and this was k alpha 1 1, and this was k alpha 1 1 minus 2 1, and this was k alpha 2 1 minus 3 1. So, let us write down the equilibrium equation. 1 which is acting downward should be equal to k alpha 1 1 plus k alpha 1 1 minus 2 1. Similarly, I can also write k alpha 1 1 minus 2 1 is k alpha 2 1 minus 3 1. I can also write k alpha 2 1 minus 3 1 is 0. This equation 1, equation 2 and equation 3. So, from equation 3, since k cannot be equal to 0, alpha 2 1 minus alpha 3 1 is set to 0, which implies that alpha 2 1 is equal to alpha 3 1. Now, substituting this in 2, we get k of alpha 1 1 minus 2 1 is 0, which implies that alpha 1 1 is also equal to alpha 2 1. Substituting this further in 1, we get 1 equals k alpha 1 1 which implies that alpha 1 1 is 1 by k. So, now I get alpha 1 1 is 1 by k, alpha 2 1 is also 1 by k, and alpha 3 1 is 1 by k. I get the first column of my influence coefficient matrix. Let us move on to the second figure. The second figure was indicating like this, delta equals unity here, which implies k times of alpha 2 2 minus 1 2, k times of alpha 1 2 and k times of alpha 2 2 minus 3 2. Writing the equation, 1 will be equal to for this, k times of alpha 2 2 minus 1 2 plus k times of alpha 2 2 minus 3 2. Then the second equation says k times of alpha 2 2 minus 1 2 is 0. Then we say k times of alpha 1 2 is k times of alpha 2 2 minus alpha 1 2. Call this as equation number 1, 2 and 3. So, from 2, since k cannot be 0, alpha 2 2 minus 1 2 is 0, which implies alpha 2 2 is equal to k times of alpha 2 2 minus 3 2 is 0. Which indicates alpha 2 2 minus alpha 3 2 is 0, which says that alpha 2 2 is actually equal to alpha 3 2. In 1, we say that alpha 2 2 minus alpha 1 2 is actually equal to 1 by k. So, substituting this in 3, alpha 2 2 minus 1 2 is 1 by k. So, alpha 1 2 is actually equal to 1. So, therefore, alpha 2 2 is 1 by k plus alpha 1 2 is 1 by k plus 1 by k, which is 2 by k, and alpha 3 2 is also equal to 2 by k. So, now this gives me the second column, alpha 1 2, alpha 2 2, alpha 3 2. Alpha 1 2 is 1 by k, alpha 2 2 is 2 by k, and this is also 2 by k. So, that is my second column of my influence coefficient matrix. Let us do the third figure. So, delta is unity here. So, this implies k times of alpha 3 3 minus 2 3, which implies k times of alpha 2 3 minus 1 3, which says alpha 1 3. So, writing the equations of equilibrium, 1 is equal to k times of alpha 3 3 minus 2 3 and k times of alpha 2 3 minus 1 3 is k times of alpha 3 3 minus 2 3, k times of alpha 1 3 will be k times of alpha 2 3 minus 1 3. Equation 1, 2 and 3. So, from 1 it says that alpha 3 3 minus 2 3 is 1 by k. Substituting this in 2, we get k of alpha 2 3 minus 1 3 is equal to k times of 1 by k, which is 1, which implies alpha 2 3 minus 1 3 is also equal to 1 by k. Substituting this in 3, we get k times of alpha 1 3 is k times of 1 by k, which means 1. So, alpha 1 3 is 1 by k. So, alpha 2 3 is 1 by k plus 1 by k, which is 2 by k, and alpha 3 3 is 1 by k plus 2 by k, which is 3 by k. So, now I get alpha 1 3, alpha 2 3, alpha 3 3 as 1 over k, 2 over k and 3 over k. I get the third column of the influence coefficient matrix. So, the influence coefficient matrix is derived directly as explained, and that matrix, which I call as alpha matrix, is a 3 by 3 matrix, 1 over k, 1 over k, 1 over k, 1 over k, 2 over k, 2 over k, 1 over k, 2 over k, 3 over k. So, this is symmetric, diagonally dominant and square. Okay. So, this is the influence coefficient matrix, which is directly derived. Once I derive this, I can also write this matrix as 1 by k of 1 1 1, 1 2 2, 1 2 and 3. For the given problem, if I write the mass matrix from this figure, it is easily m 0 0, 0 m 0, 0 0 m, which can be also said as m times of 1 0 0, 0 1 0, 0 0 0. So, now I have alpha matrix, I have mass matrix, which is m times of 1 0 0, 0 1 0, 0 0 1,